Alright, here is another sine problem, kind of like the last one. So this is our third little video segment here. I'm going to try and move a little bit quicker. Hopefully you guys are getting me so far. But say we have a sine hanging. Again, get a nice round 10 kilogram mass. And this time, let's say the two strings that are supporting it are two strings that are both at an angle, and they are both at the same angle here. So let's just say we'll use 40 degrees again. The angle that both strings make with the horizontal is 40 degrees. So, equilibrium problem. So how do we start? It's a sine. The sines generally don't move. So we can say the net force in the x is 0, and the net force in the y is equal to 0. And we again need to figure out what the tension in both of these are. Now they're at the same angle. This means that there's no reason that either one of them should have a greater tension, should have more force in it than the other one. So since the angles are equal, we'll say since theta 1 is equal to theta 2, that just means that angle is equal to that angle. That means that T1 and T2 have to be equal to each other. So if we find one, that means that we find the other. But both of these forces are pulling at that angle. Now both of these forces are also pulling upwards as well as outwards. That's what it means to have a string at some angle like that. But again, this is equal to this is equal to this for obvious reasons. And the fact that they have the same angles here makes this problem a lot easier. If these were two different angles, this would be a problem that we really wouldn't be able to do very well. So, what are we thinking here? The sine has weight. That weight pulls downward like that. That means that this weight has to be supported in equal parts by these two y components. So all we really have to use here, if we want to, there's a few different ways to solve this, but I guess the easiest would be if we look in the y direction, that we look at how many vertical forces there are. There's 3. There is the weight of the sine, there is the vertical component of the one tension, and there's the vertical component of the other tension. In the horizontal, there's only 2 forces, this one and this one. So we can just say T1x plus T2x. Now, for this problem, if we're just looking for what these two are, if we don't want to use this equation, we really don't have to, because we can kind of figure it all out from here. So, T1y and T2y, the vectors are the same, their angles are the same, so it goes without saying that these two are going to be equal to each other. Like I said, each of these strings in equal parts are taking half of the weight of this. Now, those of you guys that are really with it might just do that in your head. It's like, well, the weight of this is 98. That means that this has to have 49 newtons of it, and this has to have 49 newtons of it. And that's really what this equation comes out to. The weight, because 10 times 9.8 is 98 newtons. These two things are equal to each other, so you can just call it 2 times Ty. It could mean either that or that. And so you wind up solving that for Ty. You can call that negative since it's going downward. That is a y there. Winds up just equaling 98 divided by 2. So just as we predicted, the y component of each of those is 49 newtons. Sorry if you can't read my handwriting there, but that says 49. Now that's not our final answer. We need to know what the tension each of the strings are. We need to know like what the hypotenuse is. So let's just look at one of those triangles really quick. So there's your tension. You know, this angle is 40 degrees. Again, I'm just drawing a slightly bigger version of what we had over there before. And we now know that that vertical component is 49. And anytime we know an angle and a side, we can figure out all parts of this, all parts of any right triangle. But we really just need to know what that is. So the way I think of it, just look at it in terms of your y component equation. Your y component equation says that a y component of a vector is equal to that vector times sine of theta. Same thing we've been doing for a number of weeks now. We know what that is. We know what that is. We want to solve for what that is. So solve this for t. We do a little bit of algebra there, and we wind up getting ty over sine of theta, or using the numbers that we've already got, 49 newtons divided by sine of 40. Plug that in our calculator. And you get an answer of a little over 76 newtons. And that's our final answer. 76 for that, 76 for that. Now again, if these were two different angles, you would not be able to solve this nearly as easily. But because we can make the assumption, it's not even an assumption, it's something obvious, that, you know, this is equal to this, and this is equal to this. And again, you could do a lot of this in your head. 98 newtons is pulling the sine down, and each of these are supporting half of it. They'd have to be, since they're at equal angles. And we don't even need to fuss with the x equations. It stands to reason that this x component is equal to this x component, so that they also add up to 0. But we didn't even need to fuss with that to figure out the hypotenuse, what the tension in the lines are. So that was our second type of sine problem. Hopefully you guys are able to follow along there, and hopefully this is starting to be a little bit simple for you. But there'll be a little bit of practice for you in the second forces packet, which I think just force to add another angle or something along those lines. But you'll see, there'll be a short assignment.